Okay, so thank you everyone for coming tonight. So today we have another talk on formally verifying RISC-V zkVM constraints, which I guess is a bit of a follow-up of sorts on the one Devin did in December, but this time talking about both OpenVM and I guess some more recent work on Pico, which is ongoing. Petar is from Nethermind, who've been doing basically the most work on this kind of task, as well as other work in Arcade and other places for which there are talks which everyone should go and check out. And I'll let Petar take it from here and show us more of the cool work that Nethermind does.
Yes, thank you, Alex. So I'll talk to you about the work that we at Nethermind have recently done to verify OpenVM and Pico. So basically, the way I'm going to structure this is first I'm going to focus a little bit on sort of what we did do and specifically what did we not do, because this is a time where everyone claims formal verification for everything. So I think some clarity on the boundaries would be appreciated. And I'm going to stay quite general throughout the talk in the sense that we've done some things with the Lean RISC-V specification that was automatically extracted into Lean from the sales spec. So I'll talk a bit about that, what we've done there. I'll talk a little bit about what does it mean to enable some sort of general reasoning about buses and bus interactions in the ZK infrastructure. And then what does it mean to verify actual individual opcodes, and then some details on OpenVM and Pico verification that is happening currently. So let's start by saying what we are and what we are not doing. So we are verifying for correctness of RISC-V opcodes at the opcode level. So basically, we are providing Lean proofs that this RISC-V zkVM, whichever you want, implements the behavior of the RISC-V opcodes exactly as the RISC-V specification tells us. Our source of truth is the official RISC-V Lean specification, which was extracted from the sales spec as part of another EF grant by Galois, Lindy Labs, Cambridge, and others. And basically, at a high level, the way that we perform this verification is that we extract constraints and the bus information from the relevant air of the zkVM, and then prove that these constraints imply correct behavior. These constraints actually, and the bus interactions, especially the bus interactions, imply the correctness of the opcode implementation. There's a bunch of things we're not doing, and there are some assumptions that we're working under. So first of all, we adjust the RISC-V specification to follow the relatively recent TF recommendation for standardizing the RISC-V target architecture. We'll discuss that in a moment. We assume that the theory and the implementation of the lookup argument that the zkVM uses and the associated bus interactions is correct, so we don't prove that the lookup argument works as it's supposed to. We assume that the theory and the implementation of the underlying proof system is correct. We don't prove that either. We assume that the RISC-V specification itself makes sense with respect to the official RISC-V standard, and we assume that Lean's kernel is actually correct. So, actually, if anyone has any questions, just feel free to interrupt, because I think we have a lot of time, and I can clarify. So just go ahead if you have. This is a good point for questions about these assumptions, perhaps.
I guess, will you elaborate on what you mean by the correctness of the lookup arguments and bus interactions? Or maybe you can elaborate a bit more about what you assume.
Yeah, so we do not prove that the lookup argument as formalized in whichever paper is actually correct, that it means what it means. We simply assume that we have a bunch of bus interactions that are either carry a positive or a negative multiplicity, and that the verifier sort of accepts all of that when they are balanced, and that's it. We do not prove that there is a balancing. We do not prove that the balancing actually means that has the cryptographic properties underneath.
Okay, so you assume that they are balanced I guess, the interactions. Or
Yes.
Okay.
So for some, it's easy to prove. Like for OpenVM, you can see that they are balanced, sort of. But this is not. This is outside of the scope of this.
Okay, thanks.
Mm-hmm. Okay, so now this is interesting because I don't think anyone has seen this. I don't think I've talked to Alex about this much either. But basically, what does it mean? What are we doing with the RISC-V specification? So what do we do? So we have this core RISC-V specification that's automatically extracted, and what we do is we adjust it so that it aligns with the EF recommendation for the standardization of the RISC-V target infrastructure, which means specifically that we only have machine mode. We do not model interaction with the environment using various system calls. The memory itself is thought of as flat. There's no paging, there's no memory management, there's no CLINT, there's no PMP. And in a recent twist, misaligned memory accesses are allowed. So we actually take and modify the RISC-V specification itself to get this. And additionally, for some of the basic opcodes, two of the registers, concretely the MISA and this MSC CCFG, have to actually exist in the RISC-V machine itself. Otherwise, the RISC-V machine will not be able to execute, for example, JALR and the various branching instructions. So we just state an assumption that says that the RISC-V machine actually has these registers. And this basically more or less looks like this. I'm going to take you a little bit through the lean just so you see that it's not particularly dramatic, but it is sort of working with the real RISC-V specification. So basically, this state here is the RISC-V state that carries all the registers, that carries all the memory, that carries everything within the RISC-V state. And we are saying what? We are saying that when we read the current privilege from the state, we get privilege machine. So we have machine privilege. And there is another technical detail that says that, for example, that there's a certain bit of the M status register that needs to be unset, so you can't override the privilege. So we had to do that as well. When the memory is flat, so we have a single, there's something called a PMA region with base 0 and of sufficient size. And this is sort of zkVM specific. So for Pico, it's like, I think it's like koala bear plus 3 for what's it called? For OpenVM, it's 2 to the 29th. So it's basically specific, but specific to a zkVM. But this process is general, and you can say, we just have one PMA region of this size, where everything is readable, everything is writable, and misaligned is allowed. There's no host target interface, and these two registers that I mentioned exist. So I don't know, has anyone of you actually worked with the RISC-V specification? So you sort of have an idea of what this is and just how complicated working with this specification is. Has anyone got any experience?
I had a looked complicated. Derek worked using it.
Mm-hmm. Yeah, so basically there's a lot of monadic operations, there's a lot of unfoldings, there's a lot of corner cases, and basically when we were doing this for the first time, we sort of, and it is pretty much also what Succinct did when they were working through their memory related and control flow related opcodes, is basically you just assume some things to survive until you get to the end of the function, like for example write memory or read memory, and then you go back and you see whether or not these assumptions make sense. And luckily all of these assumptions do make sense and are independently somehow aligned with what EF is recommending, so that is a good sign. So on
Peter,
top of that,
can I ask you a quick question?
uh-huh.
So Yoji mentioned we've been working a little bit with the RISC-V spec. I wondered if you could elaborate a little bit on the motive for these adjustments that you made to the RISC-V spec. Yeah, like for example, making the memory file. Is it a simplification?
So there's a document. There's a document somewhere on the EF website that says if you want a RISC-V zkVM to run to do Ethereum, then this is sort of what we would expect you to have. I think Alex can elaborate on that actually. So these are all coming from there.
Yeah, this is Kev's work, right?
Yes, this is correct. So this is Kev's work, who leads the zkVM team, and we, after some discussions basically with Kev and others, we kind of set out to have a standard that we would like all RISC-V zkVMs to conform to, or at least a minimal target. They are allowed to support more than that minimal target, but we wanted them to support a specific minimal target, which would be enough to support the gas programs that we want them to support, as well as having some alignment in terms of compiler use, so that, for example, we can try to upstream at least a tier 2 Rust compiler that would support that minimal target, because otherwise they were all using different custom tier 3 targets, which was a bit annoying.
Okay, that makes sense. Thank you.
Yes, so basically this all comes from there. We have luckily not had to do much invention on top of that already. So now, on top of that, we build, for some of the opcodes, for actually the ALU opcodes, we separate the monadic computation of the specification and the pure computation of what the operation actually does. So if you've worked with a spec, you know that there is this execute R type that does some monadic stuff, then does the computation. It's not clear how interleaved this is, etc., etc. But basically for these, let's say, these opcodes here and all the other arithmetic opcodes, we have this execute R type pure, for example, that isolates the pure part of the computation, and then we wrap that into, let's say, an execute R type prime that first does the monadic bit and then does the pure computation, then gets stuff back, and improve equivalence. And so basically in this way, we sort of separate the monadic bit from the pure bit. And this just gives us more clarity in proofs. More interestingly than that, we have recently identified sort of the 6 basic operations on the RISC-V state that's sufficient to specify the behavior of all of the opcodes. And these include, they are here, reading the program counter, writing the next program counter, reading a register, writing a register, reading to memory, reading from memory, writing to memory. And here with the reading and writing to memory, you have this memory width. This is a 32-bit one, so you can write a byte, you can write a half, or you can write a word. For 64, you can also write a double. And there is just the detail concerning dependent types here that says that the value is a bitvec of the appropriate width. And so basically, all of these operations, these 6 operations, are enough to specify what the RISC-V opcodes from, at least from RV, 32IM, and 64IM do. And so how do we do that? So basically, all of these are operations. And so these operations, when given a RISC-V state, these operations are going to produce some kind of effect. And one of these, there are 2 types of sort of effects. We can learn something from the reads, or we can change the state somehow with the writes. And this is what is here with the operation effect. So basically, we either have some hypotheses that we keep learning, and we have the state, the RISC-V state, and see how it changes. So for example, there's this operation effect that has this result and an entry, and basically, so you have a result, you have an entry, so this result is the operation effect, and you have whatever operation you want to do on this state, really. And so basically then you check whether or not your state is okay, because this has to be wrapped in this result. If you are okay, then, for example, here I give read reg and write reg that says, if I have a read register, reg val, that means that I now know, so I've learned, so to my hypothesis, I will add that the contents of this register, and there are some manipulations here, but it's not interesting, the contents of this register reg is actually this val. And when I write in this sort of result of operation effect, I change the state to be the state that results, like from our initial state, I write the value val into register reg. And so basically, and so similarly, we can see here from memory as well. If I say that I read from an address, say a half word val, that means that in the memory itself, and you can see that here, state mem of address and state mem of address plus 1, you have some data, and these are just bytes that combined together, this bit here gives you val. And similarly, if I write the value val into memory, then I extract the appropriate bytes and write them into the state here by inserting them into memory. So do you have any questions here? We just have some operations and we just have their effect on the RISC-V state. Is this sort of okay? Lack of questions means it is.
Sounds good to me.
I
And
have,
so
I have
then-
one question which
Uh-huh.
might I have one question which might be a dumb question. Does this admit does what you're showing admit like a generalized proof strategy that can be applied for all opcodes, for example?
So if yes, I mean, I think you will see that very shortly.
Right. Okay.
Yes, I think you'll see that very shortly. So basically then, if I have a list of operations, I just do a fold del over these starting from an initial state that has no hypotheses. And this is what sort of, given that I have a list of operations now that do some things on the state. And then I think you were hinting at this probably. So this is what add is. For example,
Perfect. Yeah.
I read the PC, I read one register, I read the other register, I write the PC to be +4, and in the register I write the add. For example. This is what branch not equal is. So I have these values from the register. So basically, what does it say? I read the PC, I read the value of the register, this R1 val, I read the value of the other one, R2 val, and then if they are equal, my increment is 4, otherwise it is this immediate that is passed to the instruction, and my next PC is PC val plus increment, and that is branch not equal. And this is store half, for example. I read the PC, I read the registers, I write the next PC, and then at the address R1 val plus this immediate sign extended, I write this data, which is basically the 2 lower bytes of this R2 val. And this is store half. And so now we can prove the following equivalence. There is this execute instruction function that we do, which basically says, given an instruction, which is now a real RISC-V instruction in the RISC-V specification and the state, executing this instruction means writing the PC +4 into next PC, and then actually executing the instruction fully using the RISC-V specification. So this is what it means to execute an instruction. And then we prove that So you remember this spec add. Here is spec add, these 5 things. So basically then, sorry, was there a question? Or just an unmuted microphone? Doesn't matter. Anyway, so then we prove that if we assume the hypotheses that we learn from here, from here, then executing this instruction is exactly yields the same state that is sort of given by the execution of these operations on the state. And this is the equivalence. This is the equivalence of add.
Just so I can understand the big picture. So it's the idea that you have like the sale RISC-V spec and it's pretty complicated. And what you're doing is adding these kind of, I don't know, these primitives that can be composed nicely, and you prove equivalence of those, of your kind of rewritten spec with the original one, but your rewritten one is kind of maybe more amenable to verification. Is that fair to say?
Yes, it's going to be much easier.
Okay. I guess
we've gone a few levels up, basically from the grunge of the RISC-V spec, and now this is the following slide. So basically, we don't have to deal with all the complexity. All we now need to do is, for example, I have an add in my zkVM. I do not need to go into the details of whatever it is that the spec does underneath. All I need is to connect it somehow to these 5 operations. So basically, my goal now has become from proving full equivalence with the RISC-V spec. It's now at this higher level, at this higher layer, where it just means find a way to describe the zkVM behavior in terms of these operations. And then when you do that, prove equivalence at that level.
Yeah, okay, great. And then another follow-up is that in your equivalence theorem, you say, like, assuming you have this kind of state that's derived from running this doing this fold L. I guess in this case, like that hypothesis state, that's like, is that something that can be like vacuously, like just infeasible? Like, can you get like is there any concern that you could get like a vacuously true theorem? Because you have
no, there isn't, because it's all. I mean, the thing is that you can if you write nonsense here, but you don't write nonsense here. So you could say read PC val and then read. Well, actually, it's difficult. You could create false here, but these do not create it.
Okay, yeah, I mean, it just seems like, probably not. They seem like very small and easy to sort of see that.
It is because, and they also, so the thing is, hypotheses are created from the reads. So I can, for example, create a false list of hypotheses that says like, read register R1. Well, because
it's not I don't think it's like a real concern.
It's not, but it's a very good, it's a good point. And I'm just trying to think, like, you have to like read register R1 something, then write register R1 kind of something else, but then you also need an additional hypothesis that they're like not equal. And then, for example, you read register R1 again with the same value, and you know they're not the same, so this has to break, but you have to have extra hypotheses. So this on its own is not enough to cause a contradiction. But you could if you wanted to, but you need additional hypotheses. So this layer, as is now, does not give you that. This layer does not give you that, meaning everything is consistent. So from there, the next question is, how do we actually get the zkVMs to talk about these operations? And the answer is, so at least it was for OpenVM and for Pico, to use the buses, because everything happens on the buses, and the only way that the changes to the state happen is through the various buses that the zkVMs use. And so for that, we create sort of something like a general bus entry, like a type class, that you instantiate and that carries a lot of information about what happens on the buses. And so what does this class have? Ooh, half an hour already. What does this class have? So a general bus entry has its multiplicity, and it's, for us, it's like -1, 0, or 1. This was quite enough for I mean, that's the values that we consider. This was enough for OpenVM and Pico, and presumably for other ones it will be as well. Where a negative sort of means I am reading something from the bus, and positive means I am writing something from the bus. Various buses carry various types of data. So here you have the data length and then the actual data. I will show you what the bus is, like later with an example. And then there are 3 types of constraints on these buses. One are axioms. So this is something that we do not prove in the lean development, but we sufficiently believe follows from the Rust code. So for example, this is in transpilation, for example, there are alignment restrictions on the program counter that do not appear in the constraints, but we know that if anything is accepted by the verifier, then it has to be that something is aligned. And so this is one axiom. Another axiom is, for example, the program counter is less than a certain value always because of the field, because of the finite field wrapping. And so these are not. So axioms are things that you know hold in your infrastructure, but are not part of the specific like subset of this infrastructure that you're using, that you're transferring to lean. Then there are something that I call externals, which are sort of things like if one chip calls another chip, then it has to be that the caller chip satisfies these externals because the chip that is being called needs them, but doesn't have them on its own. So these are sort of external to a given chip, but internal to the infrastructure that we're using. So there is an example like, I will show you later the ALU chip of Pico, for example, and you will see what this means. And then there are these well-formedness properties, which is like an invariant, a classical invariant on buses. So basically, within a given chip, within a given air, if you assume that the invariant holds on all the reads, then it must hold also on all the writes. And so these are the sort of well-formedness properties. And so the well-formedness properties are assumed when one reads and asserted when one writes, whereas the externals are the opposite. They are assumed when one writes and they are asserted when one reads. Is this making a reasonable amount of sense? An example is coming.
I can imagine how to use it, but I have one question like, in buses, like some superior cycles can happen. Like somebody can remove A and add B, and somebody else can balance this by removing B and add A, and there can be just this happy cycle. And given a good proof, somebody else can add this kind of superior cycles, and still the multiplicity checking or lookup would be happy. How do you deal with this kind of possibilities?
And who is this someone else, and where is this happening?
The malicious prover.
The prover. This is outside of the scope.
Oh,
the prover
but
can do whatever the prover wants.
Yes, indeed. But the circuit needs to make sure that whatever malicious prover does, either the verifier says no or there is an execution, right?
So I think this is at the level of the proof system itself. We are dealing only with the constraints and the bus entries that appear like within these constraints. We are not touching the prover. We are not touching the verifier. We are assuming they are going to work correctly.
Yes, I can assume that.
Yes.
Still, a malicious prover can add a spurious cycle. You know, the malicious prover just needs to find some chips that, consumes A and adds B, and another thing that consumes B and adds A. Like just create a cycle.
Yes, it could, but then it would also have to do that for like all the other bus entries that happen, and there is certain balancing happening on the other side. So I am actually not sure how this connects.
So
This story.
yeah, so there can be two strategies. Like one way is to say like this kind of cycles cannot happen. You can prove that. If you can prove that in the soundness proof, then I mean we don't have to think about the cycles that cannot exist. Another way is that if there are cycles like this, you can remove these cycles, and still there must be from a malicious proof you can create a good proof by removing those cycles. That's another way to deal with it. And I was wondering which strategy you took.
For me, this is out of scope still.
Oh, okay, that's very interesting. I have to think about this a little bit. Like, I mean, even if the proof system is perfectly working, I can the malicious prover can try to find emits and consumptions so that it balances. Yeah.
It can try, but I'm not sure that in this specific infrastructure, there are like things that will balance out like that easily without a bunch of other things having to balance out. But this is an interesting question I think this is an interesting question to understand in principle.
Yes.
But I will just show you. I will continue showing you what there is.
Yes, please.
And then you can tell me sort of how it connects to your thoughts, etc.
Okay.
So basically, I'm going to come out of the presentation and show you.
On the bus entries, can you go back? I must have missed what the difference is between the well-formedness and the other assumptions.
Yes, this will be clear now.
Okay, good.
This will hopefully be clear now. So let me get here. And so right now, I'm going to show you actually what the ALU, like the ALU sort of bus of Pico does. So there's a multiplicity, it carries an opcode, and then you have three sets of, like the two operands, the B and the C, and the result of the operation A. And this is all on a bus entry. Okay? So now, the serialize we ignore for the moment. So you have, again, the opcode, the result, and the two operands. And then you have no axioms for this specific bus because there is nothing happening in the infrastructure that I care about. The externals are something. So the ALU chips get called, for example, by the CPU chip. And so the CPU chip, when it calls the ALU, it has to ensure that these hold. Otherwise, the constraints of the ALU do not mean what they're supposed to mean. So for example, these are the externals. So if I'm calling a chip, what do I have to pass to it in order to know that what it gives me back has the meaning that I think it has? And so, for example, when I call the ALU chip, if my multiplicity is not 0, then I have to have the opcode in a certain range. And if I am not, and if this opcode is greater than 4, then I also have to have done a range check on the operands, on each byte of the operands, because the ALU, like the ALU errors that write these entries to the ALU bus, they do not do this check. And so those are the externals. So this is like, what do I have to, what must hold on my end when I call something else, so that this something else has the meaning. And the well-formatness properties are simply, in a sense, the meaning of the bus. And this is ALU bus spec, and this is it. So I'll go that one. So basically,
Oh, got it. Okay.
yes.
So it like lifts those kind of field values to like the machine words and stuff like that. Like okay.
Yes. And so like I have to know that the result is in range. I have to know the operand is in range. And for example, for like 0, 1, 2, 3, 4, these are plus minus XOR and OR. They guarantee the range of the operands. They do the bus checks, but the others don't. And if I don't have that range of the operands, I cannot prove that the shifts are correct. I cannot prove that the divs and the mulls are correct. I can't prove anything. So these have to come externally. So these are the externals. And what's really great about this specific bus is that it gives like really great modularity to the proofs. So basically, you never repeat the constraints of the ALU, of the multiplication, which is complicated. You just put the ALU bus entry there. You read the ALU bus entry, and then by having it, you know its meaning, and you don't have to like inline the constraints, etc., etc. So this is done in Pico, and this is done also, I think, in SP1, because Pico is a tiny bit of a fork, at least was initially, and OpenVM does it slightly differently with a different sort of type of modularity. And so I hope that this clarified things a little bit. And then from there, we still need to figure out how to describe what these like bus entries do to the RISC-V state. And so we have like a structure. This is now in Pico. It's similar for OpenVM. We have a structure called bus row that contains the various entries per row. Then we describe what it means, what these bus operations, like how to translate the contents of these buses into the operations as seen before in the RISC-V spec. And for example, for the CPU chip, the CPU bus operations for Pico are, so these bus operations on whatever it is we extracted from the actual code, and followed by the writing of the next PC column into the next PC register. And so now, at least for Pico, we have a way of transforming bus entries together with the CPU air logic into these operations of the RISC-V specification. And then similarly, oh, sorry, this is, I think this is not a relevant slide, actually. And so, at this point, what do? We start verifying all the, if that's a message in the chat, I can't see it.
Yeah, I raised my hand to ask a question. So for, say, the ALU chip, you have an extraction of the air that takes some polynomials that are applied to the sort of register polynomials in the proof system, and enforce that the ALU is being executed correctly, right? This is part of your extraction of OpenVM to lean. And from a certain perspective, the polynomials that enforce the bus interactions are not really different, but I can't tell from your presentation of the buses whether you're actually extracting those polynomials in that infrastructure, or if you're just like kind of modeling it in lean on its own, and what the connection is to the actual OpenVM bus.
Oh, okay. Yes, we're getting there.
Great, thanks.
Yes, we're getting there. So basically what happens when you want to verify?
Question. When the CPU calls the ALU, so there is a tuple that's sent and received, do they contain some kind of timestamps?
The ALU does not. Other buses do.
Oh, the ALU does not.
No.
So when the CPU calls the ALU, in twice in a very similar way. The same argument, the same operation. Okay. The same argument, the same operation. You don't have to distinguish this. That's clever. Interesting. Okay. Thank you.
We don't
Yeah,
have to distinguish it for the ALU. This will happen on the execution bus and the memory bus of OpenVM. This will happen on the memory bus of Pico as well. The timestamps where you really need the consistency, where you need the
That
chronological.
makes sense. Okay.
Whereas the ALU operations are pure, right?
Yes, the ALU is pure. So you
And
don't
so in fact, this is basically memorization, actually, right?
Makes sense. Okay.
And so what do we actually do when we want to verify an opcode? So first we have to implement whatever transcalation from the ELF to the sort of either the bus entries or the constraints of the framework. We'll see what that means. We identify the error, then we really extract the constraints and the bus interactions by piggybacking on here the symbolic builder of Plonky 3. So we really extract, you get in Lean automatically extracted from the Rust tests a representation of these constraints and a representation of the bus interactions. So there's nothing that we sort of model there. These are really, like, we don't introduce any assumptions. These are the constraints as per the tests and bus interactions as per the tests. I hope that answers the previous question. Does it? Whoever was asking about that just a moment ago.
You got yes, you got a thumbs up from him.
Okay, I just have the screen, so I just have the presentation. I don't see what's going on in the background. So then, so when we were working with Succinct on the SP1 verification, we had these. We still had. We worked with just the columns, which was becoming more and more difficult to work with as the chips were getting more complicated. So we no longer work with the columns explicitly, but we have a layer on top. We've built a little ZK infrastructure that allows us to transform the constraints, like from that column form and bus interactions as well, into a sort of a human readable form where it's sort of you get a lot of correspondence between the between what you see in Lean and the actual Rust code. And then you can sort of, it's just like a sugaring layer on top that allows you to, instead of talking about like main of 356, you actually know that this is the variable, I don't know, x3 in Rust, and you just see it like that and you reason about it like that. And like, this was a very, very important part of the infrastructure. Then, for whichever bus interactions and constraints come up in the air, we have to prove the various statements about external zone one-formedness for each air. And then we prove that the RISC-V operation effect of the opcode is actually the same as the effect of its bus interactions. And now I can show a little bit. Well, it's going to be still relatively high level, but I can discuss a little bit about Axiom and Pico. So basically, OpenVM, what does it have? It has this transpiler from RISC-V to OpenVM, which we formalize. It has a program bus that carries the instructions and the program counters. What's interesting about Pico with respect to the others, OpenVM with respect to the others, is that it does not have a central CPU chip. It has an execution bus. And this execution bus carries the information about the current program counter and the timestamp. And then every chip interacts with this execution bus, reads the current, writes the next program counter. The timestamps of the execution memory buses sort of, you get the consistency through the standard argument through the balancing, and we've actually proven the consistency assuming the balancing in Lean. The memory bus of OpenVM also is expressive enough to talk about registers and memory separately. This is in contrast to Pico, where there's a little overlap, and I'm not quite sure what happens in SP1 now. But what's interesting about OpenVM also is that there's not that much interdependency between chips. So it feels like, to me at least, perhaps some more modularity could have been done there, but I'm not quite sure where to, like, if this is an actual critique or not. So what we've done is we've verified the 45 RV32IM opcodes, we verified the execution memory consistency, and we did not find any particular issues during this process. What does the equivalence look like here, given all the stuff I've talked about previously, is basically that. So this is, for example, for load word. Why did I choose that? I'm not sure, but there we are. So if we have an air, that's the load store air, and then for every row of that air that is like within the air itself, and if this row is not a padding row, and if all the axioms hold, if all the well-formedness holds, so for OpenVM we didn't have externals, we didn't need them. So if all the axioms hold, if all the well-formedness holds, if all the constraints hold, and then if you have, this could have been earlier, if you have that your expected opcode is 528, which corresponds to LW, and you have that the bus effect hypotheses hold. So this is the same as the operation list effect hypothesis. So these are the things that we learn from the buses by reading. And you have the RISC-V assumptions, which basically are those constraints that I showed initially. Then if you execute this instruction here, that is the load with these parameters, which come directly from the program bus, then executing that in the RISC-V spec has the same effect as what the execution of the memory bus do for that row, like what the execution and the memory, how do I say that? What is the effect of what happens in the execution of the memory bus? Given that also this memory bus also manipulates the registers. But this is the point. So we, on the one side, we have this execute instruction. On the other side, we have this bus effect. And if you remember from way back, here we had, on the one side, we had execute instruction, and we had this operation list effect. And so how do we prove this? We just move from this execute instruction to this. There are some additional lemmas to prove, and then we just basically end up comparing two lists of operations, which is relatively straightforward. It's much more straightforward than working with the RISC-V spec directly. When it comes to Pico, there is also a transpiler and the program bus, but we have a central CPU chip that executes instructions, as was the case for SP1. There is something that I call the state bus because it's registers and memory, but there is an overlap in this bus because if you put the address less than 32, then you're going into the registers, otherwise you're going into the memory. And this bus is timestamped as well, so you get consistency, but this means basically that you, for some reason, you can't really write to the memory that's below 32. And while this is an interesting choice, I think it's based on the fact that normally the RISC-V machine does not use this memory, but I'm not quite sure why that choice is there, really. And so we do get consistency from the timestamps, and Pico has this really great modularity where the chips communicate via buses, which made the proofs much simpler than for OpenVM, I think, at least in my experience. We verified all the RV32IM opcodes. We are waiting for RV64IM to land to start verifying that, because actually, if you remember those, the layering of the RISC-V spec, we actually have both for the 32 and the 64-bit for all opcodes, so we can verify 64-bit relatively straightforward. We found some minor niggles in the constraints, but that is nothing particularly notable for the moment. We have let Pico know, and they are taking care of it. This will come out eventually. And with this, actually, here's the correctness theorem for Pico and for the same instruction. And If you squint, this is the same thing. There are the externals. There's a little bit of difference how the values are there, but actually these operations have different names, but this is actually the same. Correct, Steve. So with that in mind, thank you. And if you have any questions, please go ahead. I will get out of the presentation now.
I found the answer to my own question. So the execution bus contains a timestamp and that prevents those spurious cycles. So
oh, excellent.
It doesn't have to be unique. So yeah, exactly.
I was curious how long the effort took, like a couple weeks, a week.
And for which one?
For both, I guess.
No, so it's for OpenVM, it took us a few months. And for Pico, like RV32IM was kind of like 1 month and something.
Got it. I imagine it'll only get faster with like improved.
I mean, it depends on the infrastructure, whatever comes next. You know, if these are like Plonky 3 and relatively clean, I don't quite know how the others are designed. Like if Airbender comes in with their specific ISA or whatever it is they have, then that's a very different.
Yeah, Airbender, we've worked with on Airbender a bit, and it is a bit tricky because there's probably like the assumptions that you have to add are like a bit more. There's like more of those because the whole infrastructure is kind of spread out over multiple stages. So there's lots of things that get deferred to later in the.
And for example, Zisk, I still don't quite know what they are up to because they have their own. They are not doing like a one-to-one sort of. They're not doing one-to-one mapping from opcodes to the from RISC-V opcodes to Zisk opcodes. They're doing some compilation tricks. They're compiling them. The Zisk instructions seem to be more expressive, so they can do more. So there's like, and there's a whole compilation thing in there. Yeah.
I was also curious what took the most amount of time when doing it. Was it the writing the proofs themselves?
So for OpenVM, it's sort of because we were learning quite a lot in the process. For OpenVM, it took us a long time to get these RISC-V specifications out, like to prove equivalence with the RISC-V spec, because we had to, like, we didn't quite have that EF document, and then we were just rummaging around through the RISC-V spec, and that took a long time. The proofs themselves, I mean, as the complicated opcodes, the complicated arithmetic opcodes, their proofs take time. For Pico, it's mostly opcodes because then we had the infrastructure for the buses.
Great, thank you. I was curious if you could also share any of those like kind of minor issues that you mentioned.
So, for example, there is like that state bus where under 32 is registers and over 32 is memory. When you actually go into memory operations, you're missing a constraint that you are greater than 32. So it would kind of allow you to think you're writing to memory, but then you'd be writing to the registers. But I do not see how this can be of any, like, in order to do that, you would need to have a meaningful RISC-V program that actually works with the addresses 0 to 32. And sort of from what I know, that's the ROM starts at higher than that, and like that space is just unused. But that is a question. I think also that could be a question for SP1, given the inheritance of the infrastructure, but it does not seem particularly worrying. That's one.
I guess this is also covered if like somebody tries to access the biggest possible address on a misaligned basis. so that the access overlaps into the first zero.
So there is the misaligned accesses are not supported, so you're not.
I see. Okay.
I mean, the VMs don't support them themselves, so you're not going to get an overflow,
okay,
or a wrapping, or whatever that thing is.
If I can ask one follow-up question on the operations used to specify all the opcodes, were those chosen with any of the details of Pico or OpenVM in mind, or were they just like, are they generically, would you expect them to be generically?
They're generic. There's no Pico or OpenVM
Totally
in them.
generic.
This is completely separate. This is just on top of the RISC-V spec.
Cool.
Cody, what are you saying about Airbender? Like, which opcodes are they not implementing? What is that?
Yeah, I provided a link here that shows the test failures. So it's not just fence, which already
fence I don't necessarily care about, but these other four I kind of do.
Yeah, I forget. These are large aggregate tests with lots of subcases, so it's like some kind of signed cases inside of these. I can't remember.
These are signed cases, yes, because Malach and
I think I thought for their system, they like their zk sync OS. There's like an assumption that they won't use signed any kind of signed arithmetic or something, right?
Yeah. So, but whatever, you have to modify. You have to modify the spec, I guess, or
yeah.
Yeah, but then what exactly am I trying to prove, and which RISC-V programs do I want to run?
I agree.
I mean, I can. There's no issue. I can just like the proofs for these won't work. That's it. And then if your program uses these instructions, it's not going to work. So I'm not quite sure. What Alex? What is their L1 fantasy? Have they got one?
It's a bit mixed. Originally, they weren't that interested in L1 proving at all, actually. And then at some point, they did actually obviously start submitting proofs on these proofs, and maybe they've gotten a bit more interested, but they are very opinionated about just doing their own thing and doing custom whatever. So it's a bit hard to read.
Including like auditing dependencies to make sure that none of these unsupported instructions pop up, doing whatever. Yeah.
Yes, that's a big concern.
But they will pop up. Like there's very little chance they won't. But anyways, yes. Yeah. Anything else? Anyone?
All right, I think that probably covers it all then. So yeah, very, very nice talk, I have to say, actually. I enjoyed this a lot. I enjoyed the interactive lean aspect as well. So that's very cool. Yeah, so then I'll stop the recording here. The talk will be up on YouTube later today. And for anyone who's listening, the next talk will be on the 27th, and that will be a slight shift in that we'll be hearing about verifying LLVM to RISC-V compilation, and then there'll be more kind of compiler talks in the end after that. But yeah, this was really nice. So thank you a lot, Peter, and obviously thanks to Mind for many of the very good projects they've led as part of this whole thing.
Thank you.
All right.